and I'll do a brief blurb of your CV, Rebecca.
Thank you.
Um, so Dr. Rebecca, today it's really an honor to have Dr. Rebecca Nealon to join us for present her research on accretion disks and planet formation disks. And Dr. Nealon obtained her PhD from the Monash University, and she later on became a prestigious Stephen Hawking Fellow and Assistant Professor at the University of Warwick. But now she's back to Australia and back to Monash. So great to have you around.
Thank you so much. I just want to check before I start, can you hear me clearly and can you see me as well?
Yes. Yes.
Perfect. Because during the talk you might need to see my hands. So if at any point you can't see my hands when it's clear that probably you should be able to see them, please yell out. I also want to invite you guys to yell out if you have questions during the talk, particularly if you're online. I'd much prefer to be interrupted and to have a discussion than to hold everything till the end. Thank you very much for the introduction, Chelsea. And I want to say how much of a pleasure it is to be joining you guys remotely and for having the opportunity to present some of my research. Yeah, I've recently moved back to Monash as a future fellow. My expertise as a researcher broadly lies in simulations of accretion disks, but my fellowship is in particular is about protoplanetary disks. To do this kind of research, I use a number of different tools. The first one of these is the Phantom SPH code. So I'm one of the lead developers. This code was invented by Daniel Price, and it's key for allowing us to do these 3D hydrodynamic simulations. And you can see an example of one of those here. The other tool that I use is MTFOST. It's a rapid radiative transfer code. This code allows us to take the outputs from our simulations and turn them into synthetic observations so that we can compare what we see from the simulations to what we see from the observations. And that allows us to make really rapid progress in what we're doing. The third tool I use is RICO the ring code. RICO is a 1D code, and by that we mean that we describe the evolution of the disk just as a function of radius only, and it allows us to examine the effects of warps and dust together. I'm going to talk about both of those elements, but it allows us to do it for long-term evolution in a really fast sense as well. So I'm going to be using these three things during today's talk to tell you more about, hopefully, how warps and how dust and warps placed together contribute to the onset of planet formation. So to start, to set the scene, I know that you guys know a lot about planets because of George and Chelsea, but I don't exactly work on planets. I work on something slightly adjacent to that. And the story starts with these protoplanetary disks. So the first question that we have is, what's a protoplanetary disk? This movie I'm about to show you is quite old. You might have seen it before. It starts looking at the Milky Way and it zooms in. And this movie is from about 2015. And it was a press release from ESO from when the Atacama Large Millimeter Array, the ALMA telescope, kind of first turned on and first started getting our images. The reason I like it is because as you zoom in, you get a sense of the true scale of what we're looking at. Here we're zooming into, I think it's the Taurus region. And if you see my cursor, you can see as we zoom in closer and closer onto one of these stars, this is HL Tau, you can see there's this little jet that's coming off. You've got this warm envelope of blue gas surrounding it. It's blue only because it's warm. And then as we zoom further and further and further in, you see that we have this accretion disk. Now, broadly speaking, an accretion disk is the swirling gas and dust that appears around a compact object. Accretion disks are fundamental in the universe because they are the manifestation of the conservation of angular momentum. So you see accretion disks around black holes, you see accretion disks around young planets as they're being born, but most importantly for my research, you see accretion disks around young stars, and that's what we're looking at here. So this is a disk of swirling gas and dust, and in this image, what we're seeing is the dust. And the thing that's really interesting, you've got your star hidden at the center here. The thing that was incredibly interesting about this observation when it first came out is that it wasn't flat and boring. You can see that we've got this beautiful structure. We've got these kind of dark regions here. We've got rings that you can trace and gaps in the disk. And this level of substructure was just not anticipated, really not anticipated before these kinds of observations started coming about. And some people would argue in the last 10 or so years that perhaps this is the biggest step forward that we've been able to take in our understanding of protoplanetary disks in order to actually have a telescope that's powerful enough to reveal these substructures and to show us actually what these disks should be looking like. I would argue, however, that's not actually the biggest thing that we've done in the last 10 years. To me, from my perspective, the biggest thing that we've done is we've been able to compare the observations and the simulations. So on the left-hand side is an observation of that protoplanetary disk, HL Tau. And on the right-hand side is a simulation by a colleague of mine, Giovanni Di Piero from 2015. And in his simulation, Giovanni took a protoplanetary disk and he put 3 planets into that disk. He let the disk evolve, and then he generated the synthetic observation using this process that I mentioned before, using MCFOS, this radiative transfer code. And what we see here is that actually there's a pretty good comparison between what we see in the simulation and what we see in the observation. And the implication becomes, well, the cause of this substructure that you see on the left-hand side, perhaps that is driven by planets in the disk. And so by being able to compare the simulation and the observation, we can infer some of the things that may be or may not be happening in these disks. So since its first light, ALMA has taken beautiful images of a number of systems. I've just lost my mouse. Hold on, where is it? I don't know where it's gone. That's fine. Hold on. Oh, sorry. No, that's not what I wanted at all. Sorry, everybody. Okay. I'm going to make do without my mouse for the moment. Sorry. So this image here, these postage stamps that you have here, are from one of the first big surveys that was conducted using ALMA. It's led by Sean Andrews, and it's called the D-Sharp survey. And in this particular survey, they sampled the 20 brightest nearby disks that we had access to. And what we see is a huge array of substructure. Not only do you have substructure in all these systems, but the substructure is different. Every single one of these disks is a little unique snowflake. You've got a star, at least one star hidden at the center of these systems. And in some cases, you can see spirals. So here I really wish I had my mouse, but in the top left-hand corner, but second from the left and second from the top, you see spirals. On the far right-hand side, second from the top, you see a vortex. There's like a clump on one side of the disk. You can also see rings and gaps in a number of the systems. So far left, the third from the top, there is a ring and gap structure as well. And so, I mean, based on what we saw before, I'm telling you the one way we can get this kind of substructure is that you could put planets or some kind of a body in the disk, which then gives a strong implication that maybe what's happening here is you've got a lot of planets going on. There are other explanations for why we might have some of this substructure, but by and large, what we learned from the ALMA telescope is that planet formation either begins earlier or happens much faster than we originally thought. And by that, I mean, if even some of these disks, the structure here is caused by planets, those planets have formed much faster, or they must have started forming earlier than we thought, right? And so this then challenges our understanding of planet formation. This is why we have the EXO-ALMA collaboration that are trying to find evidence of, like, to look deeper in these systems and to find evidence of planet formation in these protoplanetary disks. But this still remains an unanswered question at the moment in the literature is exactly when does planet formation begin and exactly how fast is it occurring, such that at least some of these systems, the structure here may be driven by planets. Putting that thought to the side for the moment, though, we know we have planets, so we must have a way to actually form them. It wouldn't be a talk related to planets without this particular graph. This was taken yesterday. So far, we've detected about 6,000 exoplanets. Here across the x-axis, we're showing the period, so how long it takes that planet to orbit its host star. And on the y-axis, we're showing the mass of the planet, or at least a proxy of the mass for the planet. And so you can see the range of where these planets are and how big they are on this particular graph. I tried to query ChatGPT or Claude to try and find out how many of these planets were detected by Chelsea or by George. And unfortunately, they said no. It was too hard to try and work out. But certainly Chelsea and George have been involved in a number of these discoveries, a very meaningful percentage of these planets. And so when you think about how many planets we've detected, the key thing here to take away is that all of these planets are different, and most of them do not look like what we see in our solar system. So you can see that Earth is sitting pretty much bang in the middle of this graph, a pink dot with an E. That's our Earth, and there are very few planets that live in that space. This graph, this summary graph, is hampered by things like observational bias and detection bias and all those kinds of things. But by and large, The planets that we find are very different to what we have in our solar system, and they all are unique. Again, like the protoplanetary disks that we had before, planets are different. To understand the diversity in the planets that we observe, the answer lies in the stage before. So remembering that the planets in our solar system, for example, that is a later chapter in a very, very long story. And if we go to the earlier chapters, the one before is the protoplanetary disk. And so that's why we need to understand protoplanetary disks, because that is one of the key drivers for the diversity that we see in exoplanets. So, okay, if we have a protoplanetary disk like this, well, how do we form planets? I do apologize because I still don't have my mouse. Let's make do without it. This is a cross section of a protoplanetary disk. So we've sliced the disk in half. The star is at the middle, and on the left-hand side in this cross section, what we see is the structure of the disk in both gas and dust. Protoplanetary disks are a mixture of gas and dust, 99% gas, 1% dust. The way that I think about that is the gas is driving the car and the dust is the passenger along for the ride, and they don't get to decide where they're going. The gas is driving the car. On the right-hand side of this graph, we have the wavelengths in which you might detect different parts of the disk. And then you also have where the molecules tend to sit in the disk as well. If we go back to the left-hand side, though, the important thing to take away is that in the lower part, you have the gas structure. You can see that it's flared. So closer to the star, the disk is narrower, and further away from the star towards the left-hand side of the screen, the disk is wider. That's temperature structure, that pressure structure is driven by the flux from the star as that drops off as a function of radius. And then in the upper part of the disk, we have the dust. Now, the dust comes in a variety of sizes to make it even more confusing. So you can have dust that's very small, like millimeter or micrometer sized grains, all the way through to very large dust that's that's meter or kilometer size boulders. The small dust, that very, very fine stuff, that is really well coupled with the gas, and so it tends to be basically homogenized with the gas. In this figure, that's shown by the small black dots with the blue circles around them. And you can see they're spread pretty evenly throughout the disk and away from the midplane of the disk. They go quite up high. The larger grains, though, they tend to migrate towards both the midplane of the disk, so they tend to go down, but they also tend to migrate inwards a little bit. And so you can see those larger black dots with the blue circles, they tend to be hugging the midplane of the disk and moving inwards as well. There is a collection of some of those dust grains at what's labeled a pressure maxima. So this is one way that we can collect dust together, is by having a pressure maxima in the disk. That could be caused by substructure, for example, something that's driven by a planet. So when we're thinking about how planets are being formed, we need to think about the collection of dust. Sorry? Okay. So we need to think about the collection of dust, and there's a few different ways that we can go about doing this. The two different broad methods are a top-down approach or a bottom-up approach. The top-down approach is often referred to as fragmentation or gravitational instability, and I've got an example of this on the left-hand side. This tends to occur when the mass of gas in the disk locally means that the gas can collapse under its own gravity. So what I mean by that is we've got a simulation by my colleague Sal Ralver on the left-hand side. In the top panel on the left is the start of the simulation, and then it goes down in the left-hand panel, you can see that we're forming some structure. That's due to the fact that in this simulation, the disk is quite massive in comparison to the star. And as a result, it forms these beautiful filaments that are starting to appear, spiral arms and filaments. In the main panel, which is marked 8 orbits, you can see that these filaments eventually turn into these spirals, and then you get these little fragments developing. Those fragments can form very large bodies like Jupiter-sized things. And it's a top-down approach, as in it starts from the disk and the disk collapsing on itself locally to form these planets. It's a really good way to make giant planets. It's a really great way to make planets that are big enough that they can migrate very quickly and move inwards through the disk. And so there are some limitations of the gravitational instability or top-down approach. On the right-hand side, we have the bottom-up approach. And this idea is that you start by collecting dust in a completely different way. It comes from the streaming instability, which is one family of the resonant drag instabilities. These instabilities occur because you have gas and dust in a mixture, and they can interact with one another. And under certain circumstances, this causes the dust to start to coalesce, to condense, and to collect together. So here's a simulation showing exactly that. On the top left, you have your initial condition, and then the panels are moving forward through time. And on the bottom right-hand panel, you can see that we've got all these little tiny kind of, they're marked in yellow for high particle density. These are the planetesimals that form the first seeds that start off planet formation. And so this idea is that the streaming instability or the settling instability, which is the most general application of the streaming instability, has the dust moving through the gas and moving in such a way that this instability is ignited, and that causes the collection of dust in these systems. So the streaming instability also has some limitations though. And the big one, broadly speaking, is that the streaming instability does not work very well or very fast in the conditions that a protoplanetary disk tends to find itself in. So to show you what I mean by that, this graph on the right-hand side, this is on the x-axis, a proxy for the grain size. So small grains on the left-hand side, the boulders are on the right-hand side. And on the y-axis, we're measuring the dust to gas density that you have. So this is telling you how much dust there is in the presence of the gas. And at the top part of the graph on the top right-hand side, you have circles that are marked there. That's showing you that the simulation on the left-hand side, or an equivalent to the simulation on the left-hand side, has been run for these different combinations of the dust to gas and the grain sizes. And you see collapse. You see what's happening on the left-hand side, forming these little tiny planetesimals in the simulation. However, if you move below the black line, what you find is that this kind of simulation does not produce any collapse. You don't form the tiny little seeds for planet formation, and that's because you've moved towards the left-hand side. The streaming instability does not tend to work very well for small grains, and it does not tend to work very well for low dust to gas densities. And so what that means is protoplanetary disks, they tend to start with smaller sized grains, right? And so that makes it very tricky actually for the streaming instability to be a complete solution to explaining planet formation, even though it's our most favored instability to start with. So the second thing that we need to bear in mind is that our leading explanation of planet formation tends to not work very well under the conditions where protoplanetary disks tend to sit. Okay, there's one more thing though that we need to think about in the context of planet formation. And broadly speaking, it's that stars and planets do not evolve. Oh, there's my mouse. Do not evolve in isolation. And so these are snapshots of the simulation by Matthew Bate from the University of Exeter. And here he took a cloud of gas that like a big ball of gas and allowed it to collapse under its own gravity. In doing so, it formed all these stars. And every time a new star was born, Matthew added a snapshot, a little movie that you can see here of that forming star to this sample. So you can see a zoom in of every single one of these stars as it's being formed. You can see as this is happening that we have little disks that surround the stars. But most importantly, you can see that none of these disks are forming to show the structure that I had in the schematic earlier on in the talk. We had this lovely little cross section that I showed you. None of these disks look exactly like that. We have examples of binary star systems. We have examples of systems with multiples. We have examples of interacting systems. We have triple stars. This is a quadruple system here. Most importantly, though, we have examples of misalignments. And so here we're thinking about the 3D nature of star formation. We're thinking about the fact that there's no reason for everything to be aligned. And especially when we recall that stars are not born in isolation, they are born in families, in clusters. It is noisy, it is chaotic, and there are interactions and encounters between the neighboring systems. And these interactions can occur in a 3D way. Means that actually what we should expect is not a flat disk like I showed you before. What we should expect is something far more interesting than that. And so one of the things that Matthew found in his simulation was this misaligned or a warped disk. Again, I've lost my mouse, I apologize. These snapshots here are showing us the column density for one of the stars that were formed in his calculation. And it's showing you three different views of that particular, well, it's a binary system actually. And so on the far left-hand side, you can see that the inner part looks flat. But if you look in the middle panel, you can appreciate there's an outer part of the disk that is strongly misaligned. And so we call these misaligned or broken or warped disks. And Matthew found this just as a consequence of his simulation as it was running. However, misaligned disks and broken disks like this had been predicted a long time theoretically before this. So this is a simulation by Stefano Facchini from 2013. And in it, he has a binary star at the center of a circumbinary disk. And the binary is misaligned. The orbit is misaligned with respect to the disk itself. As a result, the torque from that misaligned binary is able to break the disk into two different sections, and you can appreciate the geometry that you can see here. So now we have developed an inner disk and an outer disk with this really interesting geometry, and these disks are basically opposed to one another. In the middle of the screen, there's a simulation by Ian Rabago from 2023. Here it's confirmed using a different numerical method, using a grid code. So you can see that this outcome is robust. It's not a numerical, it's not caused by any numerics. It is just something that's happening physically in the system. There's another way to create these wonderful 3D orientations, though, these 3D structures. So this is by using a misaligned planet. So this is a simulation by Zhou Zhu, and in this simulation, he starts with a flat disk, but he puts a planet on a misaligned orbit. And as a result of that, the torque from the planet is able to carve a gap and to misalign the inner disk with respect to the outer disk. And there's a little, oh, there it is. There's a little blob here that represents little circumplanetary disks. So that's the location of the planet. And then you have your inner disk and your outer disk, and they're strongly misaligned with respect to one another. So theoretically, we have this really strong evidence for why we should expect disks to not be flat, to have some kind of a 3D structure that is beyond, above and beyond the flaring that I showed you before, some 3D orientation. In 2015, we observed HD 142527, and this kind of changed the picture of everything. So this is a scattered light observation. What that means is it's picking up the small grains, the small dust grains in the disk, which is showing us the surface of the disk, because those grains are well coupled. They are lofted to the surface of the disk. At the center of the simulation, sorry, at the center of the observation, you have two stars. We know there are two stars there because we can see them in other observations, but here they are hidden. And then these arcs around are showing you the illumination of the inner edge of the protoplanetary disk. So this is the innermost part, and the disk actually sits outside of this observation. The thing that was really interesting, the reason this observation itself was incredibly important, is because at 12 o'clock and 7 o'clock on the clock face, you can see it's a little bit darker. And the interpretation put forward, because remember, this is the inner edge of the disk being illuminated by the two stars at the center. If you've got a dark region, that tells you that there's some kind of shadow, there's something blocking the light. And the interpretation put forward was that you actually have two disks in this particular system. It's an example of one of these broken disks. So here you have an inner disk. That inner disk is hidden in the observation. And then you have the outer disk. And that's what we're seeing in the observation, the inner edge of that being illuminated by the central stars. And the reason that you have the shadows in this particular orientation is because that inner disk is a little bit misaligned. And in doing so, it blocks the light that is coming from the two stars, casting a shadow on the outer disk and revealing its presence and its orientation. If that little inner disk was exactly perpendicular, the shadows would be at 12 and 6 o'clock on the clock face, but they're not. They're at 12 and 7 o'clock, which tells you that the disk is not exactly perpendicular. It's something slightly off from that. And so from the shadows and where they fall, we can even infer things about the geometry of that tiny little inner disk. And since its discovery in 2015, we've actually found a number of examples of systems that have evidence of some kind of a warp or misalignment or a break. And this is all based on shadows in the disk. So HD 142527 in the top corner. But then as we move across the page, we've got a system with another strongly misaligned inner disk. The third one across is TW Hydra. That has a small, weak amplitude shadow in the top left-hand corner. The far right one, there's a shadow that goes straight up and down the page. And then you've got this bright region and asymmetric region on the bottom left-hand side. And it's kind of the same picture along the bottom as well. We have a number of systems now where we have incontrovertible evidence that based on the shadows and the shadow structure that we see, that there's some kind of a misaligned or warped disk. Now, I've just told you a whole bunch of different ways in which we can form misaligned systems. So you'd think we have examples of these. We should be able to explain what's causing the warps or what's causing the misalignment in these particular systems. And unfortunately, it's one of those things that we actually really struggle to do. Because despite the fact that every single one of these systems has had bespoke 3D modeling applied to it, I think with the exception, apologies, of J1604, that despite all of that, and despite having theoretical framework to explain how these things could be misaligned or why they have the geometry they have, we haven't actually been able to explain any of these convincingly yet. And so the implication is, okay, maybe our theoretical understanding is limited here, or maybe the observations, there's more that we can learn from them. But certainly there's some kind of a disconnect where we know these systems are warped, we know these systems are misaligned, but it's actually very, very hard for us to explain. However, and a big however. Let me share an example of what we can do. So this is a simulation that I conducted back in 2018. It's of a protoplanetary disk that has a misaligned planet. So we're starting with a flat disk and there's a planet and the orbit of the planet is misaligned such that it cuts through the disk twice per orbit and it's going in and out of the disk as it orbits. In the top panel, I'm showing you the top-down view of the disk, and in the bottom panel, I'm showing you the cross-section of the disk. As we put that planet in, the planet-disk interactions drive the formation of large spiral arms. We also see that you can have a gap being carved by the planet. It's a massive planet. We chose a massive planet just because it would visually work better, but this result is also robust for smaller planets. And the thing that you notice if you look down here very carefully is that the inner disk here has tilted away from its original orientation and is now misaligned with respect to the outer disk. And it's a very subtle effect. It's quite small, this misalignment. It's small enough that actually it was predicted that this tiny, tiny misalignment would not be enough to be visible in observations. So we took this system and we generated synthetic observations using MC-FOST. This is our synthetic observation showing you the flux, the scattered light that we might see if we happen to observe this system. But importantly here, the disk is exactly edge on. So the midplane of the disk is across here, and the flared structure of the disk sits along here. And these bowls, these lobes here, represent the light that's scattered from the surface of the disk, the upper and lower surfaces. And you can see that there's a bit of an asymmetry. It's a little bit brighter on the lower side here, and that's due to the presence of the warp. If we then take this disk and we change the viewing orientation, so we just rotate the disk around, so as if we're turning it around, and keeping ourselves as the viewer here, you can see that asymmetry in the flux moves from the top to the bottom of the disk. And so over time, depending on where you are viewing it from. So the first thing that we notice is that warp disks, they are likely to have some kind of an asymmetry in their flux if you happen to see one exactly edge on. The other thing that you might notice is a bit hard to see is that it also kind of moves from side to side. It kind of does this weird little dance from side to side. So not only do you have a top-down asymmetry, there's also this side-to-side asymmetry. Now, in 2024, Villanova and collaborators had a look at 20 edge-on protoplanetary disks. And through their observations, they found that out of these 20 disks, 3/4 of them showed evidence of either a top-down or side-side asymmetry, which is very much like what we see from our observations of our synthetic observations of a small warp in a protoplanetary disk. And so the implication from this work was that up to 75% of disks protoplanetary disks may actually show evidence of a small warp. 75% is too high to be attributable to something like the presence of unknown binaries or something like that. This is really down to the disk structure that we're getting to. Since then, there have been a couple of other survey studies that have indicated that on the order of 30% or so of these systems show evidence that's consistent with having a warp. So conservatively, a third of protoplanetary disks show evidence of a warp, but up to 3/4 of them could actually have this kind of structure hiding in the observations. I'd also note that Andrew Winter recently published an ExoAlma paper where they were looking at the deviations from Keplerian motion in the disks, and they found that pretty much all of the systems in the ExoAlma sample, the deviations you have there could be attributable to a warp as well. And so it's one of those things that once you know what you're looking for, it's actually much easier to find these in the observations. And certainly it indicates that a lot of these systems have warps. So warped and misaligned disks, they're common. I would argue very strongly they are common, but they're really difficult for us to explain from a theoretical perspective. So these are the three thoughts that we had. Planet formation begins earlier or happens faster than we thought. Streaming instability is currently not a complete explanation, and warped and curved and misaligned disks are common. The research question that we have is, are these statements related? So to try and answer that, we looked at a simulation of a warped dusty disk. We tried to understand if you had a simulation, if you had a warped disk with dust in it, how would it evolve and how is it different from what we've seen before? So to start with, we need to think about, well, what happens in a warp disk to the gas? Remember that these disks are a mixture of gas and dust. The dust is just along for the ride. So what is the gas doing first? So if I take my protoplanetary disk and I introduce a warp that you can see on the far right-hand side, the structure might look something like this. To understand what's happening, though, we're going to pretend that this disk is made from a series of concentric rings. Each of these rings represents one of the orbits in the disk, and we can focus on the orbit that's shown here in red and imagine a little box of gas that's going around that orbit highlighted in red. So you've got this box and it's just going round and round and round. As that box goes around, what we see is that it experiences an oscillating radial pressure gradient. This comes from the fact that at its current location, that blue box, the orbits that are adjacent to it are quite far away from it. But if that box was to go a quarter of an orbit ahead, so it's near the right-hand side of the slide, the orbits are much closer together. And so it's feeling less of a difference in pressure than it was before. If it then continues another quarter of an orbit, the orbits are now further apart because of the geometry of the warp. They're now further apart, and so you can get this this side-to-side pressure. And then as the orbit it goes another quarter of an orbit, it's now towards the top left of the red ring. The orbits come closer together again, and so that effect has minimized. So as this little tiny box is going around, it feels this oscillating radial pressure gradient because the orbits are further and then close and then further and then close as it is going around due to that geometry of the warp. This oscillating pressure gradient launches velocity perturbations, which in turn launches this breathing and sloshing modes. What that means is that little blue box, as it's going around in the orbit, in a warped disk, it deforms. It deforms by both a breathing mode, which looks like this, breathing up and down, and then a sloshing mode, which looks like the box doing this side-to-side business. The sloshing mode is highlighted by this figure at the bottom here. So here, this is a figure from Keith Stillamon's paper in 2022. Here, Keith has taken the box. It's shown here in kind of a beigey color. It's a rectangle in his particular application. And you can see that he's actually showing you how that box is being deformed as it goes around in orbit, because each panel here is representing going around one part of the orbit. And so you get, as a result of the warp, this little gas parcel that's going around is both breathing and sloshing. And that becomes really important in understanding how the gas and dust interact with one another. So to try and explain this, I have this lovely schematic. I want to focus on the top part of the schematic first. And so here we're showing the box that I was talking about before. That's the box from the previous slide, that little blue box going around in the orbit. And the box is showing the breathing mode here. So the gas, as you're going from left to right, that blue box increases its size, its height, and then over time decreases, and then increases again, and then decreases again. It's going through this breathing mode. The dust, however, is coupled to the gas. So as the gas is doing its breathing mode, the dust is promoted to also exhibit this breathing mode. And so over time, it's also breathing. But whilst in the gas, it's going up and down all the time, in the dust, because of the velocity difference changing, it tends to collapse towards the midplane. So the gas is going up and down like so, but the dust over time collapses to the midplane. We call this enhanced dust settling. We expect dust to settle towards the midplane over time, but in the presence of a warp, because of the breathing mode, the dust should settle faster than it would otherwise. And we can look at this from a 1D perspective. So we can model that tiny little box going around in the warped disk, and we can ask the question, what is the midplane density of that box? And so I want to emphasize this is a warped, dusty shearing box analysis. And so as a function of time across the page for each of these panels, we're showing on the y-axis the density of the midplane of the box. And the point here is that the lines go up every time, right? They increase every time. The density is increasing every single time. And this is faster than what you would get for any other settling that you would normally have. So having a warp means that the dust goes to the midplane even faster. Well, if we then have a look at this effect in 3D, in 3D, we tend not to recover the breathing mode. We tend to recover the sloshing mode, right? We have these two things together. I'm showing you here two panels of the same simulation. On the left-hand side, we have the top-down view, and on the right-hand side, a rotated view, so you can appreciate the geometry of the warp. And here, we're only showing the dust, right? And so in this little protoplanetary disk, we've got a warp and dust, and over time, what you see is the formation of these rings in the dust. I'm actually not going to call them rings, though. I'm going to call them arcs. And the reason is because a true ring is connected, right? But these structures, it's like a connected ring that you've sliced in half and then you've offset it ever so slightly. And so what you see here are these arcs in the dust. And these arcs are coming from the sloshing of the gas. As the dust is settling to the midplane, which it will do in these simulations, the gas is sloshing. And so the combination of the slosh and movement to the midplane causes the dust to roll into these rings. But the slosh changes as the gas is going around. And so what that means is at the line of nodes here, where the slosh changes direction, and shown here, where the slosh changes direction, you get the ring position actually changing ever so slightly. And so we call this the warp-induced dust instability, or windy for short. It's a terrible nickname because it's not produced by wind, but it was a cool name, so we went with it. The warp-induced dust instability, where the fact that you have a warp in the disk and the presence of dust drives the formation of these beautiful arcs in the dust, and these arcs are broken at the location of the line of nodes of the warp. Okay, so we have this way of collecting dust in the disk. That's great. But we can also demonstrate that this effect depends very strongly on the size of the dust that you are simulating. So in the top left-hand corner, this panel here, sorry, is showing the same simulation, just at different grain sizes. So the top left-hand is showing you really small dust grains, and the bottom right-hand side is showing you the boulder type dust grains, the big stuff. And you can see that the rings that we form, the arcs that we form, are much stronger, more prominent in the top left than they are in the bottom right. So this effect works best in 3D calculations for small grains and not the large grains. And we can tell you why. Here's a side-on view from these simulations where you can see the gas is shown in blue and the dust is shown in red. And the dust, we expect it to move to the midplane. But in a warp disk, warps are not stationary things. They are dynamic, which makes them wonderful but very difficult to study. And what we can see actually is that the gas moves, and because the small dust in the top panel is well coupled to the gas, it moves with the gas. So as the gas disk is moving in response to the warp, the small dust follows it, and windy is very well expressed. But in the case that the dust grains are large, they're poorly coupled to the gas, and as a result, they get left behind as the gas is moving. And so you can see in the bottom panel that the midplane of the dust is no longer lined up with the midplane of the gas, and as a result, windy is not experienced anywhere near as well. So what this means is if we had multi-wavelength observations of some of these systems where we might expect windy to be occurring, that this would tell us very clearly whether or not this effect is actually prominent in the system because we have this clear observational prediction. Okay, but let's go back to planet formation, right? We now have this great way to form these rings and these dust collections just due to the presence of a warp in these protoplanetary disks. What does this mean for planet formation? If we think back to this graph about the streaming instability, when it works and when it doesn't work, it works very well on the top right-hand side, and it works poorly at the moment in the bottom left-hand side. However, windy works well across this whole graph. Windy doesn't care. It actually works best for the small grains, like I just showed you. So windy works very, very well on the bottom left-hand side, sorry, on the left-hand side of this graph. So the question that we have is, if you have a disk and a third of protoplanetary disks experience a warp, if you have a disk that experiences a warp and it generates these rings in the disk, these collections of dust, that will change where you are on the y-axis of this graph. And in general, it will push you upwards in this graph. And so the question we have is, does windy, this way of forming dust collections in disks, move you into a region of the parameter space where the streaming instability will work very well? To try and examine this, we're going to move a little bit of a gear change to larger warps. So here's some work led by my colleague Hossam Ali, and he's looking at processing disks. So here you have a disk, you start with a flat disk with a binary system, so two stars at the center, and these stars, their orbit is misaligned with respect to the outer disk. Over time, from the top left down to the bottom right, the disk processes like a spinning top, like a processing dinner plate, right? It's because it's pressure supported, it's communicating with itself, and so as a result, you see that the disk is doing this kind of a motion. It's a little bit hard to appreciate in this figure though, but that's what the gas is doing. However, the dust is not exhibiting solid body precession. The dust is exhibiting differential precession. So if we have a look at the dust structures that you see here, what you find is that the dust processes with its own local precession frequency. Instead of processing like a whole dinner plate, each dust particle is processing independently. And so the dust that's closest to the second binary stars, that's processing very quickly, but the dust that's further away is processing very slowly. That means that at some point, there's going to be a particular radius in the disk where the gas disk that's processing like a dinner plate is processing at the same speed as that particular dust grain. Where that happens, you have this interaction which produces these rings in the dust. And these, we call them traffic jams. These rings in the dust are produced without any pressure maxima or anything like that. It's just because you have the gas and dust interactions in a misaligned processing disk. We can recover this with a 1D prescription. So this graph is showing you a result from RICO compared to the simulations on the previous slide. The x-axis here is showing you the distance from the star as a function of the semi-major axis of the binary. So like on the left-hand side, you're close to the stars. On the right-hand side, you're far away from the stars. And then the y-axis here is showing the surface density of the dust. So this is showing us where is the dust distributed in this particular disk. And the initial condition is shown by the black line. Our SPH calculation from the previous slide is shown by the blue line. And then you can see the other colored lines here are showing you the result from RICO, our 1D prescription. So we can recover this kind of behavior in a 1D prescription and in a 3D code. And we infer it from a 1D dusty, warped shearing box kind of thing as well. So what this means is this result where we have these dust rings really is robust. All right, and so I just want to highlight some work by my colleague Jeremy Smallwood. So Hossein Ali walked so that Jeremy Smallwood could run. Jeremy took this idea and said, okay, like we have signatures, we have observations of disks that are polar. So here you have 2 stars at the center, and then the disk starts kind of misaligned, and over time it turns to become polar and to become exactly perpendicular to the orbit of the stars. And Hercules 99 is one of these examples. But Jeremy asked the question, okay, at some point in this disk's evolution, the stars and the disk had to be misaligned, which means that it should have experienced these traffic jams. So the question becomes, once the disk has evolved to be polar, does it still exhibit those dust rings? So he ran a simulation based on Hercules 99. And on the right-hand side, you can see that he's got the dust in his calculation. Instead of running with one dust grain, Jeremy ran with a range. And they're split by the arrows. You can see the different components that he simulated, going from 0.7 centimeters all the way up to 3.7 centimeters in terms of grain size. And this effect depends on the grain size. So you can see that he's got slightly different signatures by the end of his simulation for each of these. On the far left-hand side is a graph showing the evolution of the dust, the total dust for his simulation. So we've got as a function of time across the page, so the start of the simulation on the left-hand side and the end of the simulation on the right-hand side. And the y-axis is showing you the radius in the disk. So close to the stars is down the bottom and far away from the stars is up the top. And the color is showing where the mass is distributed. So yellow is like high density and purple is low density. And as we move from left to right across this graph, you can see the formation of these strings, these fingers, and they represent rings of dust in the simulation. And each of these different rings corresponds to different grain sizes because each grain size will form a ring at a different radius as a consequence of this particular traffic jam phenomenon. So Jeremy was able to show, okay, again, if we had multi-wavelength observations of this system, this would be a smoking gun to tell us that, that this system is experiencing this effect where you have these dust traffic jams. The other thing that Jeremy showed, however, was that as the disk moves from misaligned to polar, when it gets to polar, the engine that's actually driving the formation of these rings, the precession, cuts off. Because once it's exactly polar, there's no misaligned torque, and so there's no more precession. However, the rings stay. the rings do not disappear. So Jeremy was also able to show that as a result of this disk moving to polar, it generates these rings. And once it gets to polar, it's there. You wouldn't have known how else it got there, but the rings stay there. And so that should also tell us, how did these systems form? Did it actually go from misaligned through to polar, or did something else happen? So that's a fantastic observational prediction for what we should be looking for. Jeremy also asked the question, okay, what, like, you have these rings, does that mean they're actually favorable for planet formation or not? So on the left-hand side, I'm showing a figure as a function of time and then again radius on the y-axis. This is showing us the dust to gas, the dust to gas density. And for the streaming instability to operate, we want this number to be above 1. So we want the orange part of the graph, which you can see does occur in towards the end of his simulation. 2 of these rings do actually meet the criteria to have the dust to gas ratio that is favorable for the streaming instability. On the right hand side, he calculates the timescales on which the streaming instability should be occurring, like how quickly it should occur if it happens to be ignited. And he found that these are favorable for planet formation. So at least in this particular simulation, Jeremy was able to demonstrate that by having these dust rings, you can actually find conditions that are favorable for planet formation to occur through the streaming instability. So the summary so far is that if you have a small warp, you have this warp-induced dust instability, you have rings in the dust and collections in the dust. If you have strong warps due to misalignment and precession, you can also produce slightly different rings, but rings nonetheless, and that those rings can, for the example of of Hercules 99, can actually meet the requirements needed for the streaming instability to be favorable to be operating. So the thing to take away at this point is it doesn't matter how warped it is, doesn't matter how misaligned it is, it produces conditions that are favorable for planet formation. I now want to talk really quickly, if I may, because I appreciate I'm getting low on time, about IRIS 04125. This is a very recent result. This particular disk has been observed a number of times before, but at the end of 2024, Barber et al. Published a new paper about this particular system, talking about the detection of an exoplanet. And so I want to talk through this system. On the left-hand side, we have the sub-millimeter observation. I would call this an unimpressive observation in the sense that it doesn't really tell you, it doesn't look like it tells you that much about the system. In itself, it is an impressive observation, but the resolution, I mean, of course, it's limited by resolution. And so what we see here is there is some kind of a disk around this star. Fantastic. You can also tell from this observation the orientation of the disk, and broadly speaking, it's roughly face on. So you've got a star, you've got a disk here. The other thing to know about the system is that there's a wide binary. So you've got your primary star, you've got a disk almost face on, and then you've got another star that is on an orbit, which is at least 500 AU away. The projected separation is about 600 or 700 AU. So there's this very wide binary, and that's on a different orbit is to the disk itself. So the disk and the outer binary, they are misaligned. At the end of 2024, Barber et al. Published the detection of an exoplanet in this system around the primary star through transit observations. So you can see here these beautiful transit curves. I think they had 17 transits in the end. And when they went through the data, what they found was that this planet is about 0.3 Jupiter masses. It has a period of 8.3 days, which corresponds to an orbital radius of 0.074 AU. So it's incredibly close to its star. And most importantly, if you've detected a transit from this planet, it means that it's passed in front of the star. If the disk is almost face on and the planet is passing in front of the star, it means that the planet and the disk must be strongly misaligned. So that then becomes very interesting because you have this transiting planet. It has, and it's strongly misaligned to its disk. You have this outer binary that's also strongly misaligned. And this system is, to date, or at the time of publication, was the youngest transiting exoplanet ever observed at 3 million years old. So not only do you have this well-formed planet, it's all happened extremely quickly. This is an example of the geometry of the system. This is from Barber et al. And from the left-hand side to the right-hand side, we're going down. We're zooming down in scale. So on the far left-hand side, we're starting with the big zoom-out picture. You've got your primary star. The secondary star, that outer binary that's misaligned, is shown in the dark red. If you then zoom in on the primary star, you can see this disk, which is almost exactly face on. And if you zoom in further, you can see the primary star with this tiny little planet's orbit around it. And if you zoom in even further, you can envisage just how big this planet should be. Now, in this figure, Barber et al. Have drawn the orbit of the planet to be aligned with the orbit of the outer binary. But from the observations they have, you can't actually constrain that. All that we know it's crossing is that it's crossing in front of the star. You don't know whether it's crossing in front of the star this way or this way or this way or this way, just that it's crossing in front of the star. So you then have this very complicated system, and the question is, how do you form it? That's where we come in. And so there are a bunch of different ways that you might like to interpret this. The one that we settled on that I'm going to explain is the idea that maybe this binary system, so your primary star, your disk, there's a planet in there, and then this other binary star at a large separation. Maybe that didn't start as a binary system. Maybe it started as a triple system. Andrew Winter's done a lot of work on this particular system, this torus region, I should say, sorry, the torus region, looking at this dynamical encounters and the evolution of the stars in the torus region. And he's previously published on HV tau, where you have 4 stars in a system that then went through this chaotic dissolution. So the chaotic interactions of the orbits that you have over time, something gets ejected. And so in this particular case, you had 4 stars to start with, and they split up, and so you then have 2 binaries that somehow look like they were previously connected. And in the top panel here, you have the observation, and in the bottom panel, you have his simulation, the synthetic observation you get from his simulation. And so certainly in some circumstances, it makes sense that you might have a system that starts with more stars. You have this chaotic interaction, something gets ejected, and what you're left with is what you observe. And so the question is, like, is this perhaps what's happening in IRIS 04125? So what we want to do is to model the dissolution of a triple system. We want to start with 3 stars, have some chaotic orbits, and then kick one of them out, and so you're left with 2 stars. And to ask the question, can that recover the misalignments that we see in this particular disk? To do that, the parameter space is enormous, and so what we do is we cheat. We absolutely cheat, and we try to model this using a flyby. So we start with 2 stars, we throw a 3rd star at it, with the implication being that once that 3rd star is leaving, it's a bit like as if you had started with 3 stars and you've kicked one of them out. It's certainly not a perfect way to model it, I'll be absolutely honest, but it reduces the parameter space greatly. So that's what we attempt to do. Here I'm going to show you our best model. In the middle, we have the simulation. We're starting with the disk edge on. And on the right-hand side, we're plotting the misalignment between all the different components as a function of time. And the observation from Barber et al. And the misalignment between the disk and the outer binary that they had is shown by the dashed line that you can see there. And on that graph on the right-hand side, we're going to plot all of the different components as well. And so as the flyby star comes in to have its interaction, what we see is that the disk already starts to move a little bit, but you started with something that was basically edge on. And as a result of this interaction, this star being kicked out, you end up with something that's almost exactly face on. It's much more compact than what it was. And that's what we know from the observations. IRIS 04125 is a very compact disk. And so that is also consistent. And so what we can see here on the far right-hand side, this is the misalignment observed in our simulation. And then this is the misalignment that we're aiming for from the observations from Barber et al. The really interesting thing to pick up, though, is that we also measure up here, this is the inclination between the binary and the planet. So this is the thing that was not well constrained by the observations from Barber et al. You just don't have enough information. And in pretty much all of our simulations that were consistent with this misalignment here, what we find is that the planet is almost retrograde to the disk itself, which becomes very interesting. We repeated this kind of experiment for a number of different parameters. So across the page on this graph from left to right, we're changing which direction the flyby comes from. This makes a big difference in the dynamical encounter. And then on the y-axis, we're changing the mass of the flyby. So how massive was the thing that came and interacted or ultimately was ejected. And the winners here are the markers that are orange circles with the orange filled circles with the black circles around them. And so you can see across our parameter space, there's only a few cases of this, and they tend to occur for the lower flyby masses. And it's very specific to which angle they're actually coming from. But we do find quite a few cases where we can recover the observed parameters from Barber et al. Using this kind of interpretation, even though it's a limited interpretation because we're using a flyby to try and model what's happening in this dissolution of a chaotic triple system. Perhaps the most compelling point, however, is this. So Andrew Winter, in his previous work, he's run these n-body calculations of the torus cluster. This is where RSO 4125 is located. And in these simulations that he's run, he has been able to match the statistical averages of what's happening in torus. So we think that these calculations are representative of the dynamical interactions that's happening in this system. Within his simulations, he found 28 examples of triple star systems that decay to binary systems in the method that we're trying to see if this is ideal for IRIS 04125. Of those 28 systems that underwent this process, 16 of them occurred within the first million years. Remembering this planet is really young, we want stuff to happen fast. Otherwise, it's not good, it's not helpful for our interpretation. On this graph here, he's showing as a function of the mass ratios between the remaining and the injected and the ejected and the most massive, he's showing these 28 examples of triple systems that decay into binary systems, and the color is showing when it happened in the simulation. And our best fit model from what we have modeled completely independently of Andrew is shown with the red star. And so we can see that actually the best model that we have, the initial conditions that we kind of worked out were the best fit to the observations. They are completely in line with what Andrew would predict is potentially happening in this cluster in terms of if it was a triple system that decayed into a binary system. And so here we have this really nice confirmation that actually probably this is what's happening in this system. I don't have time to go through them, but there are other interpretations for RSO 4125. And the chaotic dissolution of a triple system, that's this one shown in the third column, that seems to match the observations the best. There are other interpretations, but they each have their limitations. And I'm happy to talk about them in questions. I appreciate that I'm over time. So to summarize, thank you very much for your attention. There's a few things to take away from today. Firstly, planet-forming disks are likely to be warped or misaligned, at least a third, if not more, have some evidence of a warp. Broadly speaking, we can't explain the misalignments in these disks, but when we do this numerical modeling, what we find is that small warps form dust rings, large warps form dust rings, and both of these are favorable to planet formation. We need to motivate the initiation, the start of planet formation. And these dust rings that we find is a natural consequence of relaxing the assumption that everything should be flat. These are very favorable for planet formation. IRIS 04125, the system that I just talked about, has this very young misaligned planet, and it's an ideal testbed for warp disks. When we talk about the modeling of individual systems, the question I always get is, well, what have you learned? Like, okay, you can explain one system, but what does that tell you? In the case of IRIS 04125, what we're invoking is this dynamical, interaction where you have this triple system that then decays into a binary. But during that time, you're also forming a planet within 3 million years. So what we're saying here is that the thing to learn from this particular system, the reason we want to understand how it has formed is because it places a very strong constraint on how quickly planet formation can occur. And that was one of our initial questions as well. If you take nothing else from today's talk, this is it. Warp disks are common, they're motivated, and they change our understanding of planet formation. Thank you very much for your attention, and I'm sorry that I've gone over time.
Thank you so much for the talk. I think
I'm
we'll quickly ask students to ask questions given the time limit.
Yeah.
We'll allow 2 questions from students.
I'm going to stop sharing so I can see you.
If you can we go over a little bit? Sorry.
Yeah, of course.
Yeah. So we'll allow students to ask questions. Please just yell out.
Yeah. I have a question. Thank you for the talk. It was brilliant. I have a question related to is there a way to predict a number or a type of planets in a disk, considering the amount of dust or gas?
Oh, what a good question. So you're saying like if you had more dust, do you predict more planets, or if you have less dust, do you predict less planets?
Yeah, for example, or just type of planets, for example, small planets instead of a giant type of gaseous planet.
I don't know. I think I think this is a great question, right? Because I mean, it comes down to how are you starting planet formation. We know that, for example, if you have a planet in a disk, that makes it more favorable to actually form subsequent planets because that can drive a pressure maxima, can drive like a pressure bump, and that is a nice place for you to collect dust. So if you have at least one planet, you can then motivate the formation of further planets. But your question is like, okay, if I have like a large amount of dust, do I expect to see a large amount, like a more massive planets or something like that? I'm so sorry because I am not sure. Can I get back to you? So I think that's a great question.
Thank you.
Thank you. I'm gonna write it down.
Other questions from students? Again, online students, please just feel free to unmute yourself and yell out. If not, we'll just open question up to the room, I think. Yeah.
Am I allowed one?
Yeah, please. I think you know the Heidi one very well.
I wasn't going to ask about Heidi. I thought that was really cool.
I thought it's really cool too.
Yeah, but I know the planet well.
Okay, I have a question, but it's okay. I'll let you.
Okay, I'm sure that you've had this question before, Rebecca. So when you say that what disks got common, can you talk about that as a function of stellar properties? So in addition to multiplicity, how does stellar flyby and things like that affect warp disk frequencies for different types of stars?
Specifically,
Yeah.
I'm curious about different mass dependence of the stars.
That's what I mean. Yeah.
Yes. Yeah.
Masses. Yes, so I think that at the moment we also don't have a good handle on this because you're basically asking, if I've understood your question correctly, how likely is a disk to be warped under certain conditions, like if it has a star of this mass or that kind of thing. Is that right?
Yeah, like most of the observations so far, observationally, we're talking about A stars, other than IRAS. So
Yeah.
when you go to lower mass stars, what's the frequency of warp disks?
Yeah, I think the reason that we don't know the answer to this is because it depends on your observational completeness, right? So, for example, there was a study by Antonio Garuffi. He's one of these people who's produced a study that says that about a third of disks should be warped. But in that case, he found that most of the warped disks also had evidence of spiral arms and they're around massive stars. And so it's like, okay, but is that because these ones are easier for us to see, or is that because it's actually more likely for it to be occurring? And I don't know yet that we actually have a really good answer for that. Yeah, what I could do is the study by Villeneuve. I don't know if she actually did have a